Hi, my name is An Qizheng, and this is my fifth lab report for the course Physics 2211 on a falling slinky. The goal of this experiment is to find out whether the bottom of the slinky stays at rest when the stressed slinky is dropped from a position at rest. I used Tracker to track and analyze the slinky's motion in the YouTube video, and I constructed a model of the motion using closed script. Then I compare the model's motion to the observed motion. Finally, there is the result and there is a conclusion. There are some fundamental principles that I use. Newton's second law. The final velocity equals to the initial velocity plus F net over the mass times delta t. The gravitational force is minus mg times j hat, and j hat is the unit vector. The formula for the drag force is minus b times v squared. B here is the drag constant and v is the speed. And finally, the position update. The final position equals to the initial position plus the average speed times delta t. Here's the tracker video. Here is the xt graph and the yt graph we get from our observation. From the yt graph, we can see that before the upper part reaches the bottom part, the position of the bottom of the slinky does not change. But after the upper part reaches the bottom part starts to fall and its y position changes. Here's the closed script code for the model. I set the bulk mass to 0.2 and I get its position vector from Tracker, and its initial velocity is 0 since it is dropped from rest. And I use two while loops here. The first one is when t is 0 to 6.4 seconds, which is before the bottom starts to move. From this calculation of net force, we can see that the total of the gravitational force and the tension is 0, which indicates that the bottom does not move. Then I apply Newton's second law to update the object's velocity and its position. The second part of the while loop starts from 6.4 seconds to 8.8 seconds. This is when the bottom part starts to fall down. The net force here is not 0 since the drag force and the gravitational force total is larger than the slinky's tension. And here's a video of how the model works. Here are the xt graph and yt graph we get from the model and observation. You can see that the xt graph is a horizontal line in both situations, and in the yt graph, the observed motion shows slight fluctuations from around 6.4 seconds, as there are some other forces I have not considered in the model. Here's the result in conclusion. So the result I get is that the predicted and observed motions are very close, but the graph of observed motion shows slight fluctuations starting from 6.4 seconds, which is when the bottom starts to fall down. And my conclusion is that the bottom of the slinky did not drop because the slinky's tension and the gravitational force are equal, which makes the net force 0. But after the upper part of the slinky reaches the bottom part, its position changes as it begins to fall. Thanks for watching.